All right, how y'all doing today? So we're going to be looking at inverse functions of the square, square root, cube, and cube root. Now, at this point, hopefully you are familiar with what a square root and a cube root looks like. If not, that's okay. We're going to talk about the inverse functions of them, and you'll see them again one more time. And I just realized I left my calculator, so let me go grab that real fast. So when we're talking about inverse functions, we are talking about two functions that relate to each other in the fact that one undoes the other one. And so, first of all, an inverse operation is something that you've kind of been doing your entire life. I'll give you some simple ones to kind of just get an idea of what an inverse operation is. If you had, let's just say you had the value of 1 and you added, and that was your starting value of 1. Let's say we added 2 to that to get the value of 3. Okay. So the question becomes, if we had the value of 3 and we wanted to know where we started at, how do we get back to our starting value of 1? Well, if we added 2 here, then we would have to subtract 2 here to get back to the starting value of 1. So that's kind of your inverse operation, which is to undo what you did to begin with. Okay. In algebra, which you are familiar with, and I'm going to kind of just make it up right here on the spot, is, if I had, let's just say I had 2x plus 4, and that's going to be equal to 8. And you're asked, well, what is the value of x whenever you try and solve these? Well, when you solve this, you use inverse operations. For example, I want to remove this 4. So I'm going to subtract 4 because the inverse operation of adding and subtracting. And I subtract 4 to both sides to balance the equation on both sides. And then I divide by 2 because this is multiplied by 2. So I divide by 2 here, which means I divide by 2. And we come to the fact that the value of x is 2. And what I've done is I've done two inverse operations, one which is subtracting 4, and then one which was to divide by 2 in order to get to the value of 2. And what that tells me is that in order to get the value of 8, I had to multiply 2 times 2 plus 4, which gives me the value of 8. Okay. So that's kind of what an inverse operation is and does and why we use it. The inverse function, however, is along the same lines as what I did here with this particular set. But you look at it in terms of what does undoes what specifically. So for example, you have x squared. The inverse operation of x squared is the square root of x. You have the square root of x. The inverse operation of the square root of x is x squared. And why are those two go together? Well, again, going back to my original example, if I had x squared, so like for example, if I had 2 squared, that would give me 4. But if I wanted to go backwards to get to the original number, then I would square root 4 to go back to 2. So that's why these two are the inverse operations of each other, is because one undoes the other one. Okay. If I had x cubed, the inverse operation is cubic of x. If I had the cubic of x, cube root of x, then the inverse operation would be the x cubed. For the same reason that I did up here. If I cubed a number, then I could cube root it to get back to the original number. Okay. The most important thing to get out of this, at least right now, is the fact that this notation is used to denote the inverse of a function. Okay. So f of x and then f of negative 1x. So that's the function. That is the inverse of the function. Okay. If that's the function, then that is the inverse of the function. Okay. So there are some rules in terms of the inverses for squares as they are compared to cubes, and we'll get to those in a little bit. But one of the questions is, how do you know if two functions are actually inverses of each other? Well, there are a couple ways of doing this. Graphically, there's a way of doing it. There's a way of doing it by understanding domain and range. There's a way of doing it by actually solving the equation. There's something what we call composition of functions, which we're not going to worry about right now, but we'll worry about that later. So what I'm going to show you first, what this is really going to focus on is the graphing aspect and the domain and range aspect of the two functions to determine if they are or not. Okay. So the first thing I want you understand is graphically, for two functions to be inverses, they are going to reflect over the equation or the line of y equals x, which is the line that goes through like this. Okay. And what happens with this line is you have two functions. I'm going to highlight them for you. You can kind of see that reflect. I'm going to make this one peak right here too. Make that a little bit thicker over that line. And it actually does something to the domain and range. Okay. Okay. So you have this line here, this blue line, which is y equals x, and then you have this function, and then you have this inverse function that reflects over it. Okay. Here you have this function, and then you have this inverse function that reflects over it over here. Okay. And they both reflect over this line of y equals x. Okay. Now in a calculator, what you can do, and again, now if you want to see if these are functions or not, is this. If I go to y equals, let me see if I can get this to focus because it's losing focus. And I put the first function in, let's just say the first one is x squared. Just kidding. And the second one I look at is the square root of x. Okay. You can hit graph, and what you will see is this graph here and this graph here. Now, they may not look like they are functions just by looking at this right here. If I throw in the third equation that is called y equals x like this, and I use something called a zoom 5, this one right here, the square zoom, what it will do is it'll give me the function, that function, and then there's my line of y equals x. And so they are inverses of each other. Okay, just kind of like that. I could do the same thing with the cube root, make this a cube, and then make this the cube root. Graph it, zoom 5, and see that my two functions are inverses of each other graphically because it looks like they reflect over that y equals x line right there. That just happens, okay? So graphically, you can tell, looking at the graph, the table is just like this, okay? But here's the other part to the graph and why that y equals x line is so important is because of this. And this is the part that you really want to pay attention to is this. If I pick a value, okay, let's just say I pick, let me see if I can find one that's nice and neat. Nope. Nope. None of these are nice and neat. That's kind of the hard part about it. Well, okay, I'll do this one right here, I'll show you. I pick a value, okay, like let's just say I pick this point here. That looks like it's, 1 something right there. That point also exists on the function, or I'm sorry, if I pick a point on the graph here, it also exists on the function here. So that's roughly about almost 1, 3 point. This is not the best graph to do this on, by the way. I think one's about right here. So it's about right here that I'm looking at. Okay. You have 2 points that exist here and here that are the inverse points of each other. Okay. So here's basically what it means and what that happens. Okay. If I were to figure out the tables for these two graphs, okay, then what I would notice is this. Okay, and this is the other part to the graphing of the line itself, is that your domain and ranges of inverse functions are the opposites or the inverses of each other. Okay, so for example, if I had a table that this was the actual function, okay, we'll just call this the function for now. Okay, then this might be the inverse. Now, first of all, notice that this is f of x and g of x. That's okay also. It doesn't always have to be f of negative 1x. Okay, it works by naming them two different letters. But here's what I do want you to notice. If the point exists on 2, 4, then on the inverse function, the point exists at 4, 2. Interesting. If the point exists at 5, 6, then the point on the inverse would exist at 6, 5. So on and so forth. Okay. And so one of the rules, or what really happens, is that the point, this y equals x line, what it really says is this. If I know that the table has a value of 2, 4, and my line that I reflect over is y equals x, then basically it says this. If my value of x is 2, therefore my y here would also be 2. If my value of y is 4, then my value of x is also 4 on the inverse. And that's what y equals x actually does. Okay. It basically switches your x and y values in order to develop and create the actual inverse of the graph. Okay. That's what an inverse is and what's an inverse. That's one way to prove that two graphs. So if I go back to my original graphs here, like this, and actually go to the tables, what I will see is if I pick a point, like say right here, if I pick negative 2, 8, right there, then I go to where negative 8 is, and I see that there's a negative 2. See? Okay. And again, if I pick another point, let's just say I pick, let's see, oh, that's 2, 8. Here's 327, right? So if I go to 27 on the x, I should see a 3 on the second guy. There it is. Okay. So that means that these two are the inverses of each other by proof of domain and the y equals x line graph here. Okay. So now how do you actually draw and create an inverse? Okay. So what you do is this. You take your graph and you get some point off your graph that you have. Like for example, I'll pick the point here, the pivot point. Okay. And I will say that is what, 3, negative 2. I'll pick this point right here, which looks like it's 5, negative 1. I'll pick this point right here, which looks like it's 1, negative 3. Okay. And then I'll pick this point right here, which looks like it's 7, 6. Okay. So that's this graph right here that I have drawn here. Now, if I want to create the inverse graph of it, here's what I do. Because of the y equals x line, I can take my values and say, okay, if this is x and this is y, therefore if x is 1, therefore my y has to be 1. And my y has to be my x now. And I can do that all the way through by reversing my domain and ranges. So now I can take these points that I just wrote, and regraph those. There's 1, 2, 3, 4, like that. And then the other one that I'm going to do is this one right here, which was negative 1, negative 10. So negative 10, negative 1 right here, kind of like this. And what it's going to do, it's going to give me a graph that looks something like this. And you can see that there's a reflection that goes right through this line, kind of like that. And you've created an inverse graph, okay, by using the inverse property of your domain, y equals x domain switch, okay? Pretty nice, pretty simple, right? Now, there is a way to do it from the equation if you're not sure. I'm not going to do that right now. Maybe I'll do it in the next one, but we'll do this one here first. And that's to solve this for x. But for right now, I'm going to do this, show you with the graph. Calculate, okay? So again, if I want to take this, I plug it in. Cube root, x plus 1 minus 3. Okay. And I go to my table again. then I can go, let me go up. Let me get some small, nice numbers here to work with. There we go. Let's do, hold on, let me get rid of this one right here. This one's throwing me off right here. Looks like we got -2, 0. And again, I'm just going to kind of write these down. -2, 0. -1, -3. 0, -6. And then let's just pick one more somewhere. What do we got? 7, -9. Okay. And I can graph those. Here's this point. -1, -3. 0, -6. 7, -9. Kind of like that. And if I just hit graph real fast, I can kind of see what it looks like. So then this looks like this, sort of. Okay. So if I want to graph the inverse part of this, I just take my x and y value again because of y equals x and switch my domain and range values in order to actually graph the inverse part of this. So 0, -2, -3, -1, -6, 0, -9, 7. And then sometimes, I need one more point to finish this off nicely, but sometimes, if, you can get some really nice artistic things, and that was a little off. But again, you should see kind of a reflection along those lines like that, okay? Now, the other way to do this that you could do, besides graphing it, is to actually solve this through. And I'm going to show you this. If you understand how to do it this way, that's what I would focus on. But I'm going to show you how to solve this one anyway, kind of like this. Let me get a piece of paper to write on real fast. So if you get it, you get it. If you don't, I'm not overly concerned. But it's like this. Okay. I'm going to change this to y equals 2x minus 2 squared, cubed, plus 1. Okay. And I'm going to solve for x. And to do that, I would subtract 1 to both sides. Divide by 2. And then because this is cubic, I would cube root the entire side. Then I would add 2 so that my final function looked like that. And this would be the inverse equation for this guy, okay? So try it real quick. Try and see if you can draw the inverse based on this right here. And again, I'll show you the steps. Again, if you want to try it this way, go for it. If not, stick to the calculator, do it that way. I'll be back in a second so you can kind of get it. Okay, there's what that looks like. Again, I got these points off the table here, just like this. I plugged the first equation in to get it. Okay. All right, so now square roots. This one's a little different because this one requires you to be able to do what we call a domain restriction. Okay. And that basically means that I'm not going to graph the entire thing on this. Okay, so here's basically what happens. When you have a domain restriction of 0 to infinity, what that basically means is I'm only going to graph this part of the equation itself. Okay, and there is a reason for that. So the domain for this guy is negative infinity to infinity. The range for this guy would be 0 to infinity. So I'm only going to graph that side right there. So 0, 0, 1, 1, 2, 4. And then the other one would be 3, 9. case you really want to have it. Okay. So if I do the inverse side of this, 0, 0, 1, 1, 4, 2, 9, 3. And the reason being is because the inverse of squared, x squared, is the square root of x. And so when I graph it, 0, 0, 1, 1, 4, 2, 3, 9, it looks something like this. Okay. Now, the reason why we restrict the domain on this has to do with the fact is that we are square rooting. So in order to get the correct graph here, the square root of x, okay, does not square root negatives. Okay, so in other words, if I were to do this side of the graph, that's where all my negative values exist. So if I try doing the square root of -1, square root of -2, we're not going to get the other part of the graph because we're not taking square roots of negative. Those are imaginary, if you remember from past tense. So we're not going to square root that. Therefore, on a quadratic, we have to restrict its domain because we will not be square rooting negatives. So we're only going to restrict the domain to the right side of the graph in this case in order to create the square root function, which looks like this. Okay. Now, the domain of this guy is going to be 0 to infinity, which should look very familiar to the range. And if you remember what I said a minute ago about how your domain and ranges are switched because of y equals x, your domain and ranges are switched because of y equals x. Now, the range of this one, however, also goes to this because that's the parent function for it. So it's a little different for this one, but I could take this one step further. I'm not going to in terms of what we call plus and minus. But we have to restrict the domain in order to do that. So that only occurs if you have an x squared value. And let me do that. Okay. So if I have this guy, right, and I want to do this, I go to my calculator and I plug him in, x plus 3 squared minus 2, and I go to my table. The domain restriction says, the domain restriction says that I want it to be from -3 to infinity. Okay. So what I'm going to do is I'm going to graph this first. So -3 to infinity. So -3, -2, -4, -1. Oh, sorry, I did that backwards. -2, -1, and I don't know, 0, 7, because why not? Okay. So I'm going to use this to graph the first equation. So -3, -2 is right here. -4, -1, 0, 7 is somewhere up here. -2, -1 is right here. So the first graph looks like this. Okay. But I'm going to restrict its domain to -3 to infinity. And what that means is if I go to my table, then the only thing I'm going to look at is just this part of the graph right here, this side. Okay. So I'm going to look at -3, -2 as one of my points, which is going to become -2, -3. Then I'm going to look at the next point, which would be -1, -2. Then I'm going to look at the next point, which would be -7, 0. And I think I skipped one here in accident, but 14, 1 would be a good one. Because all of these are going to fit my domain restriction that is this side right here. Okay. So if I regraph it, this was a bad one by the way, but I used it. So now it's at -2, -3, which is right here. -1, -2 is right here. 7, 0 is right here. So my graph is now going to look something like this. Okay. And that would be the inverse part of that. And I apologize if that's a little confusing. I'm not trying to make it confusing. But that's what a domain restriction does and is. It takes only part of the graph for the domain and regraphs it for the inverse because, again, it's the square root of the graph. So my domain here would be -infinity to infinity. My range would be -2 to infinity. And since my range is negative to infinity, that is going to actually become my domain. And my range in this case would be negative 3 to infinity. Which again, if you notice that domain restriction becomes my new range for the actual piece.